Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio visual quality, everything is clear so that we can proceed for the session. Before we start this session, let me tell you what is the ideal duration and what is the agenda for today's session. Friends, the ideal duration for today's session is going to be approximately 45 minutes. And the agenda for today's session is that we are going to talk about the basics of transmission line. And this session is going to be important for all the electrical and instrumentation students who are preparing for HPCL 2023 examination. Sorry, it should be 2022. It should be 2022. HPCL 2022 examination. For all electrical and instrumentation students, this session is going to be very important. I am going to discuss some of the important problems and I will be explaining the related concept also, so that if you get a similar question in the examination, you are able to handle those questions. So everybody just tell me in the comment section, are you ready? And before we start, just everybody like, share and subscribe the session. Just like the session. Share it with your friends and colleagues and subscribe to BYJU'S Exam Prep so that you do not miss any of the important session for your examination. Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from BYJU in 2010. I have written a couple of books and these are my areas of expertise. Before we start the session, one important general session I am going to take, and that is going to be 21st of July, and the timing is going to be 9 p.m. in the evening, in the night. And this session I will be discussing that how you can make winning as your habit. That if you follow some simple tricks, if you follow some simple principles while you are doing your preparation, you can win every examination, and believe me, it is going to work. So if you are interested in this session, just set the alarm right so that you do not miss this session. It is going to be very important for your preparation. Let us understand what is the agenda for today's session. Today's session will be talking about the problem practice for designing part of the transmission line, performance of line and reactive power compensation. We'll see how much time we have, how much bandwidth we have, and accordingly we are going to discuss the problems. Let us see the first question. The first question talks about what is the main advantage of bundled conductor. So I am assuming you all are familiar with the concept of bundled conductor. If not, let me give you a brief idea. If you talk about the types of conductors, types of transmission line conductors, what is the first type we can have? The most simple type, that is going to be single solid conductor. Single solid conductor. It is going to look something like this. It is nothing but a long circular cylindrical construction. That is what we are calling as single solid conductor. The second type of conductor we are having is a stranded conductor. Then we have bundled conductors. And the last one is hollow conductor. Now let us understand the story behind different types of conductors we are having. For the single solid conductor, what is the main disadvantage? Can you tell me in the comment section? Everybody just tell me. What is the main disadvantage of single solid conductor? The problem is skin effect. Skin effect is going to be very high in case of single solid conductor, and I hope you understand what is skin effect. What is the advantage? The advantage is mechanical strength is going to be good in case of single solid conductor. But we want to overcome this disadvantage. We want to reduce the skin effect. In order to reduce the skin effect, what we are doing? We are using a stranded conductor. Your stranded conductor is going to look something like this. We are using a small cross section strands like this. And there are basically two types. Either it can be, you can say all aluminum conductors, okay, where all the strands are going to be of the same material. Or you can have ACSR conductors. ACSR conductors means the core conductor or core strand is going to be made of steel. Because even though you have reduced the skin effect by using a smaller cross section strand, but still some skin effect is going to be present. And skin effect says that there is a tendency in the AC current to flow near the surface of the conductor. It means the core strands are not going to have significant current. So in order to increase the mechanical strength, what we are doing? We are removing the core strand that is made of copper or aluminum, and we are putting a steel strand. That is why it is called as steel reinforced aluminum conductor. But this stranded conductor is also going to have a big disadvantage. What is that? This conductor is going to have significant amount of corona. Corona is going to be very high. Why corona is high? The problem is, you see the surface of this stranded conductor is going to be not smooth. It is not smooth. It is going to have sharp corners. And you know that at the sharp corners, the electric field stress is going to be very high. And when the electric field stress is very high, corona is going to be very significant. In order to reduce corona or reducing the electric field stress at the surface of the stranded conductor, we are using bundled conductor. What we are doing in bundled conductors is still, instead of one conductor, we are using number of smaller conductors and giving some spacing to them. We'll discuss more about bundled conductors. And then in the last we have hollow conductor. Hollow conductor, we are having something like this. At the circular circumference, we are having strands of a smaller cross section. This design was proposed by a company named Anaconda, and that is why this conductor is also called as Anaconda conductor. I hope this classification is clear for all of you. Now our focus is on bundled conductors. The moment you listen this word bundled conductors, what is the first thing that should come in your mind? Yes, what is the first thing that should come in your mind? The major reason for using bundled conductor is to reduce the electric field stress at the surface of the conductor. The expression for electric field stress at the surface of the conductor is given as phase voltage divided by GMR ln GMD upon GMR. Now this is the logarithmic one, so it is not going to affect much. So if you want to reduce electric field stress, what you can do? You can increase the geometrical mean radius. So the basic idea behind bundled conductor is to anyhow increase the GMR. How we are increasing the GMR? We are increasing the GMR that instead of one solid conductor, one conductor, we are having number of smaller cross section conductors and giving them some spacing. This is 1, 2, 3, 4 and up to n. These are called as subconductors. These are called as subconductors. And this is a single conductor. I hope it is clear for all of you. And what is going to happen if electric field stress at the surface of the conductor is going to reduce? Corona is going to be less. Corona is going to be less. Corona is going to be less. But there are some other advantages of using the bundled conductors. What are they? Let us try to understand. The first thing is, if you see the inductance, it is given as 0.2 ln GMD upon GMR. It is millihenry per kilometer. Now you are saying, sir, GMR has been increased, so inductance is going to be reduced. If you see the capacitance, we are defining as 2 pi epsilon naught upon ln GMD upon R. Now we are not writing GMR here. Why? Because the GMR concept is not applicable in case of capacitance calculation. Why? The reason is, when you talk about the geometrical mean radius, you are talking about the internal flux linkage. Capacitance deals with the electric field, and you know that inside the conductor, electric field cannot be present. Electric field lines cannot be present inside the conductor, and that is the reason we don't talk about GMR in case of capacitance calculation, even though as a mathematical tool this is going to be same or similar like a GMR. In comparison to inductance, there is a slight difference. What is that slight difference? This R is going to be like GMR without 0.7788 factor. I hope you know this. When we are calculating the GMR, we are using this factor in case of inductance calculation. When you are doing the same calculation for the capacitance, the only thing you have to do is just remove this factor of 0.7788 and rest of the procedure is same. But because we know, we understand that GMR is not going to be applicable as a concept in case of capacitance calculation, so we are simply writing this as R. In some of the books, for bundled conductors, they are also using the word self GMD. So if you want, you can write self GMD also. Now if you are saying, sir, this R value is increased, so this value is going to be reduced, so capacitance is going to be increased. Is it clear for everyone? Now what is going to happen to the surge impedance? Surge impedance is going to be defined as under root L by C. Because you have increased the GMR, L has been reduced and C has been increased. It means what? The surge impedance overall is going to be reduced. The next one is surge impedance loading. That is V square upon ZC. Now ZC has been reduced, so surge impedance loading is going to be increased. Now let us talk about the stability. Let us talk about the angular stability or the steady state stability. The real power transferred is given as P max sine del. This is the approximate power angle equation. Here P max is defined as V1 V2 upon X. What is this X? This X is nothing but omega L. This L you are saying has been reduced because GMR is increased. So this X is also going to be reduced. And if X is reduced, voltages are not changing. So P max is going to be increased. Now if you have a constant power transfer and you are saying P max has been increased, it means at the same time sine del has to be reduced, or you said del has to be reduced. What is the meaning of del? If you see the power angle curve, I am drawing it here. If you see the power angle curve, I am just drawing it here. This is del, this is P, and this is going to be your approximate power angle curve. This is going to be the steady state stability limit, or this is the Pmax condition. It is going to happen at del is equal to 90 degree, and this del is equal to 90 degree is the border. Beyond this, your system is going to become unstable. You know what is the reason. If not, then we will discuss it in the stability part. And this side, it is going to be stable. It means if you operate your machine at a lesser value of del, then more and more your machine is going to be stable. So by increasing the GMR, you are getting a lesser value of del, operating condition. So your system becomes more stable. So we are saying by using the bundled conductors, stability is also going to be increased. These are several important inputs related to the bundled conductors. I hope everybody is getting this. Just tell me in the comment section. Are you able to follow this? I am not able to see your comments. And everybody just hit the like button. Yes, everyone. Tell me in the comment section, are you able to follow me? All these important inputs, you may get one small question, and I hope after this much discussion, you must be getting the confidence to solve it. Is it clear? So let us see what is the question. The question is saying, what is the main advantage of bundled conductors? So what is your answer? Reduce surface electric stress on the conductor. Increases the line reactance. This is wrong. We have seen the line reactance is going to be reduced. Decreases the line capacitance. Wrong. It is going to increase the line capacitance. Let us talk about the next question. When a fixed amount of power is to be transmitted, the efficiency of transmission increases. Now please try to understand. He is asking you to increase the efficiency of power transmission, and you know that efficiency is going to be inversely proportional to the losses. If losses are going to be more, efficiency is going to be less. If losses are going to be less, efficiency is going to be more. He wants efficiency of the transmission to be increased. So if you are saying efficiency is increasing, it means losses are going to be reduced. How you are representing your losses? Losses are going to be directly proportional to I square R. Now at the designing stage, you are going to talk about the resistance. Yes or no? When you are designing your transmission line, then you can talk about resistance. But once you have designed your transmission line, now you cannot change the resistance or any of the line constants. It means at the operating stage, if you want to increase the efficiency, then you have to reduce the losses or you have to reduce the current. How you are going to define the current? Current you are going to define as P upon root 3 V cos phi. I am writing it for a three-phase system. Now in the question he is saying fixed amount of power is transferred. Fixed amount of power is transferred means P is going to be a constant. You want current to be reduced. Current is going to be reduced only when this V cos phi is going to be increased. V cos phi increased means what? V is also increased, cos phi is also increased. What is cos phi? This is nothing but power factor. So both the voltage and the power factor you have to increase if you want higher efficiency. What is the correct answer? Voltage increases, power factor remains same. Wrong. Voltage increases, power factor increases. Right. Wrong. Wrong. Is it clear for everybody? Just tell me in the comment section. Yes, Ashish, you're right. Everybody just tell me in the comment section, are you able to follow this? Be active in the comment section, then only I can get to know whether you are able to follow me or not. Let us go to the next question. What is the function of a steel wire in ACSR conductor? First you understand, your ACSR conductor is going to look something like this. This central strand or the core strand is going to be made of steel, and rest of the strands are going to be made of either aluminium or copper. And this is the reason ACSR conductor, it is called as steel reinforced aluminium conductor. Why you are using it? You are using steel reinforced in order to increase the mechanical strength of the conductor, because using the steel strand is going to give mechanical strength to your conductor. And what is the consequence of that? Suppose you are saying, sir, mechanical strength has been increased. So what is the consequence of that? The consequence of that is, suppose if you have this type of construction, and this is your conductor, there is going to be some sag, yes or no? There is going to be some sag. How we are defining this sag? This drop in the conductor we are defining as sag, and if this is your ground, then this distance from the ground we are defining as ground clearance. Ground clearance. So what is happening? If mechanical strength is increased, what is going to happen? If mechanical strength is increased, then sag is going to be less. If sag is going to be less, obviously the ground clearance is going to be more. If ground clearance is more, it means what? The height of the tower and the number of transmission tower is going to be less. So you are saying number and height of transmission tower is going to be less. So ultimately, the total cost of transmission is going to be comparatively less. Is it clear? Is it clear, everybody? Just tell me in the comment section. Are you able to follow this? They can ask you anything, so I am trying to discuss every concept related to the question what we are having. So what is the function of steel wire in ACSR conductor? Compensate for skin effect? No. Take care of surges? No. Reduces capacitance and inductance? No. Additional mechanical strength? Yes. Is it clear for everybody? Just tell me in the comment section. Ananya, how they are connected, you don't see from inside. Okay, what you see is just a conductor. Last point you want me to repeat. See what is happening. We are operating our transmission line at a very high voltage. So there must be a minimum ground clearance. Now, if by using the ACSR conductor, you are getting higher mechanical strength, so this drop in the conductor shape is going to be less. Sag is going to be less. When sag is less, ground clearance is going to be more. When ground clearance is more, it means height of the transmission tower and number of towers is going to be less. Yes or no? Yes? Just use your common sense, you will understand. See the next question. For a stranded conductor of 6 layers, the total number of individual wire will be. Now first you understand something about a stranded conductor. A stranded conductor is going to be something like this. Now for a stranded conductor, we have a set pattern. The pattern, how these smaller cross-section strands are going to be arranged. Suppose this is what we are calling as first layer. and these 6 strands we are calling as the second layer. This is how we are defining it. So there is a pattern of strands, and that pattern follows 1, 6, 12, 18, 24, 30, 36 and so on. It means the first layer it is going to be 1 strand, second layer it is going to be 6 strand. This is going to be first layer. This is first layer. This is second layer. Third layer it is going to have 12 strands and so on in the multiples of 6. Now, if you want to know what is the total number of strands, then you have the formula. Suppose that is capital N. So this capital N is 3n square minus 3n plus 1. What is n here? N is the number of layers. So n can be 1, 2, 3, 4, 5, any value. If you see the question, in the question he is saying for a standard conductor of 6 layers. So n is given as 6. So what is going to be the total number of strands? It is 3. What is n square? 6 square minus 3. What is n? 6 and plus. This is 6 and plus 1. Just solve this. I think you must be getting as 91. So C is going to be the correct answer. C is going to be the correct answer. Everybody just tell me in the comment section, are you able to follow this? These type of simple questions you can expect in HPCL, because HPCL you will be getting around 180 questions and you have to solve them in 150 minutes. So the level of questions is not going to be very high, but you must be having a strong hold on the concept. Is it clear, everybody? Just tell me in the comment section, are you able to follow this? Any doubt, you can ask me. Now, next question talks about a stranded conductor having 3 layers, which has each strand diameter of 5 mm, and he is asking the total diameter of the stranded conductor. Now please understand, from the same diagram we can understand, or let us make another diagram. Suppose this is a stranded conductor. I am just using 2 layers. And I want to know what is the total diameter. Suppose this is capital D of this standard conductor. If I am saying D is the individual strand diameter, then can you tell me what is the relation between capital D and small d? Yes, D is going to be 3 times D. This is also D, this is also D, and this is also D. But you can have any number of layers. So we have a general expression. The total diameter of the standard conductor is 2n minus 1 small d, where n is the number of layers. If you use this formula, how many number of layers are there? This is the first layer, and the second one layer is this 6 strands. So you have total 2 layers. If you put it here, you will get D is equal to 2 into 2 minus 1 D, that is 3D. Is it clear? Just to confirm this relation. Now he is saying the individual strand diameter is 5 mm and the number of layers are 3. It has 3 layers. So what is going to be total diameter of the standard conductor? It is 2. What is n? 3 minus 1, and this is d, that is 5 and mm. So it is going to be 6 minus 1 multiplied by 5 mm. So this is going to be 25 mm. B is going to be the correct answer. Everybody just tell me in the comment section, are you able to follow this? Only one candidate is responding. I don't know what others are doing. If you're able to follow, no problem, enjoy the session. And if you have any doubt, please ask me. Yes, everyone. Let us go to the next question. Next question talks about a bundled conductor system. It is saying a single conductor of radius 4 is designed by using a bundled conductor system having 4 conductors. Let me give you a basic idea. Suppose this is your single conductor. If you want to replace this conductor by using a bundled conductor, what we are going to do? We are going to divide it into number of subconductors of a smaller cross section and give some spacing to them. This is 1, 2, 3, 4 and suppose n. Obviously all these subconductors are going to be operating in parallel, so operating voltage is going to be same, but the current is going to be different. Suppose here current is I1, here it is I2, here it is I3 and so on, and here it is IN. Suppose the voltage and current here for this single conductor is going to be like this. Suppose the radius of this single conductor is going to be capital R and the radius of these subconductor is going to be RB. I am using the suffix B to represent the bundled conductors. Now the voltage is going to be same for both the cases and we can apply the Kirchhoff's current law so that total current is going to be same. Yes or no? And you know, for transmission line, the current density is going to be constant because current tappings are not allowed. You cannot connect load directly to the transmission line. So the current density is going to be constant throughout the length of the transmission line. So how you are defining the current? You are defining the current as current density multiplied by the cross sectional area. Just put it in that equation. So you will get J into A is equal to J into A1, J into A2, J into AN, because J is constant, so it remains same. So you can write A is equal to A1 plus A2 plus AN. This A you can write as pi R square, and suppose all these subconductors are similar in construction, it means they have the same radius or same cross sectional area. So A1, A2 up to AN is going to be same, so I can write N multiplied by pi RB square. Pi is going to be cancelled, so I can get the expression RB is capital R divided by under root N. Either you can remember this expression or you can write the equation and then you can get the answer. In the question he is saying single conductor of radius 4, so capital R is 4 centimeter. Bundled conductor system having 4 conductors, so number of conductors is again 4. He is saying the radius of each subconductor, so it is going to be capital R divided by under root N. So this is going to be 4, this is going to be under root 4, this is 4 divided by 2 and this is going to be 2 centimeters. Is it clear for everyone? Just tell me in the comment section, are you able to follow this? Yes or no? Yes, everyone. See the next question. Again a similar concept question, but a little bit twisted. Instead of one single conductor, it is having 2 subconductors, and these 2 subconductors are replaced with 4 subconductors. These are having radius R1 and R2. Here R2, sorry, it is R1, R1. This is R2, R2. This is R3, R3. Now I want to give you a concept so that you can save some time in the real examination. You don't need to write this whole expression because there may be little twisted questions in the examination. But what is the crux you can take? How you can make it a shortcut? No need to relate the current, because when you are relating the current density is constant, you can directly write in terms of the cross-sectional area. Even you can save some time. Instead of writing this area directly, you can write the square of the radius. Are you getting this? You can write the square of the radius. How you are going to write, let me tell you. If you are going by the conventional way, how you are going to write? Suppose current here is I1, here it is I1, current here is I2, current here is I2, I3, and here it is I3. So if I have to equate the current, I will be writing I1 plus I1 is equal to I2 plus I2 plus I3 plus I3. So it is going to be I1 is equal to I2 plus I3. Now if you relate it with the area, it is going to be A1 is equal to A2 plus A3. Write it in terms of the radius, you are going to write it R1 square is equal to R2 square plus R3 square. What he is asking is R3. So R3 is going to be under root R1 square minus R2 square. Just put the values. What is R1? 2 centimeters. R2 is 1 centimeter. So this is going to be 4 minus 1. So this is going to be under root 3 or 1.732 centimeters. This is going to be R3. So you can save a lot of time if you can directly write. The radius equation. Can you write it? Just tell me in the comment section. In the real examination, do you have that much conceptual clarity that accordingly you can write the radius equation? Are you getting this shortcut? Yes, everyone. I hope you can do this type of questions now. Let's go to the next question. A single phase transmission line has two parallel conductors 4 meters apart, radius of each conductor being 2 centimeters. Calculate the capacitance of the line per kilometer. It is a single phase transmission line, so it is going to be something like this. Suppose this is A conductor, this is B conductor. He is saying it is 4 meters apart. Suppose distance between them is D. So this D is going to be what? 4 meters. Their individual radius is same, and that is 2 centimeters. So their radius is going to be 2 centimeters. Now he is saying find the line capacitance per kilometer. What is the idea of line capacitance? Let us try to understand. In between, in the middle of these two conductors, there is going to be the neutral point, and generally what we do, we represent the capacitance with respect to this neutral point, because capacitance we are talking in terms of the electric field or the potential of electric field. Now potential is always represented with respect to a reference. Without reference you cannot talk about potential, because it is relative, it is not absolute. So we define the capacitance of a conductor with respect to the neutral point as CAN. Similarly, we define the capacitance of B conductor with respect to the neutral point as CBN. And what is the expression we are using? CAN is going to be equal to CBN, and that is equal to 2 pi epsilon naught upon ln d upon r, and this is farad per meter. But he is not asking individual conductor capacitance. He is asking the line capacitance. Line capacitance means the capacitance between A and B conductor. This is CAB. This is what he is asking. This CAB is going to be a series combination of two capacitances whose value is same. It means what? What is going to be CAB? That is the line capacitance. It is going to be CAN or CBN divided by 2. So what is the line capacitance expression you are going to follow? Pi epsilon naught ln d by r farad per meter. Just put the values, you will get your answer. Is it clear, everybody? Just tell me in the comment section. I think you must be getting A as the correct option, 5.247. Is it clear? Everybody, do not forget to like the session. It is the only motivation for me from your side, so that I can get to know, so that I can continue these type of sessions more. Anyways, let us proceed to the next question. Calculate the capacitance of a 400 kilometer long 3-phase 50 Hz overhead transmission line consisting of 3 conductors of each diameter 2 centimeter and is spaced 4 meter at the corner of equilateral triangle. So what is the construction? The construction is going to be something like this. These 3 phases or conductors of different phases, they are placed at the corners of an equilateral triangle. Equilateral triangle means triangle whose all sides are going to be same. Suppose this is A phase, this is B phase, and this is C phase. I am going to tell you a shortcut. Suppose the distance between A and B is going to be DAB, this is DBC, and this is DCA. I am just going to tell you a shortcut how to find the GMD for a 3-phase system in one sentence, one line only. Now it may be equilateral or it may be asymmetrical spacing, vertical spacing, horizontal spacing. What is the equation you are going to follow? If you want to write the GMD for this 3-phase system, what you do? Multiply the distance between A and B, B and C, and C and A, and take the cube root 1/3. Because there are 3 distances, you want GMD. GMD is nothing but a distance. You can see the proof of this also. We don't have enough time to discuss the proof, but this is the shortcut you can apply. Let me give you some idea. Suppose you have the vertical configuration. Vertical configuration is generally used in case of transmission system. For transmission lines, we are using the vertical configuration because in order to accommodate double circuit line, okay, you know what is double circuit line? When you are using 2 parallel circuits so that more and more amount of power can be transferred, stability is high, then we have to give some spacing, and for that spacing we are using vertical configuration, because for transmission line ground clearance is not going to be a big deal, because generally transmission lines are passing from those areas where there is very less population. But in case of distribution system, we have horizontal spacing, because for distribution system it is generally passing from those areas where the population is very high, so we have to maintain the ground clearance. A, B, C, A, B, C. No confusion. The direct expression you can write just in one line. You can write the GMD, distance between A to B, B to C, C to A, power 1/3. That's it, finished. Suppose as per this question, he is giving you equilateral spacing or equilateral triangle. It means A to B, B to C, and C to A distances are going to be same. It means what? DAB, DBC, DCA, they are same, and it is given as 4 meter. So can you directly write the expression for the capacitance? Yes, it is going to be 2 pi epsilon naught ln GMD upon R, and this is going to be farad per meter. Can you write the GMD? Yes. Distance between A to B, B to C, C to A, power 1/3. So directly it is 4. GMD is going to be 4. What is the value of this R? R is given as, conductor diameter is given as 2 centimeters. So what is going to be the radius? The radius is going to be 1 centimeter. Just put the values, you will get your answer. Is it clear, everybody? Just tell me in the comment section, are you able to follow this? Yes, everyone? Are you able to follow this? Let us see one more question. Find the GMR of the following ACSR conductor. See, this is not a real conductor. This is not a practical conductor. This is a hypothetical conductor, because I told you already, for a standard conductor, we have a set pattern. First layer, second layer, third layer, fourth layer, and so on. First layer, 1 strand. Second layer, 6 strand. Third layer, 12 strand. Fourth layer, 18 strand in the multiples of 6. So this is not a practical standard conductor. Obviously, it is going to be hypothetical, but because it is given in the question, so we have to find it, we have to solve it. How you are going to solve it? This is strand number 1, 2, 3 and 4. Because it is ACSR conductor, this fourth strand is going to be made of steel. And please remember this concept. In the GMR calculation, steel wire or steel strand is not included. Why it is not included? Because it does not carry any current. Because it does not carry any current. So if I have to write the GMR for this construction, this GMR is going to be GMR for first strand multiplied by GMR for second strand and GMR for third strand. What is the power? Because you need only one GMR and there are 3 GMR, so you have to take the power as 1 by 3. No rocket science, only common sense. How you can write GMR 1? GMR 1 is going to be individual effective radius of first strand, that is 0.7788 R multiplied by the distance between 1 and 2 and 1 and 3. The distance between strand 1 and 2 and 1 and 3. What is the power? How many distances? 1, 2, 3. Power is 1 by 3. Because you need only one GMR and GMR is a distance, nothing else. Can you write GMR 2? Yes. GMR 2 is going to be 0.7788 R, that is the effective radius of strand 2, multiplied by the distance between 2 and 1 and 2 and 3. So distance between 2 and 1 and 2 and 3. What is the power? 1 by 3. Can you write the GMR for the third strand? Yes. Effective radius for the third strand and the distance between 3 and 1 and 3 and 2. So it is going to be D31, D32. What is the power? 1 by 3. Is it clear, everybody? Now see, suppose each, okay, I think there is something missing in this question. Each strand radius has to be mentioned. Randomly just take any value. Okay. Okay, it is asking in terms of the R. So you have to find the factor. So suppose this is R. This is going to be 2R. And this is again going to be R. So what is the distance between 1 and 3? D13 or D31. This is going to be 4R. This is R, this is 2R and this is R. Now what is the distance between 1 and 2 or 2 and 3? So this is going to be 90 degree and this is going to be R and this is going to be R and this is also going to be R. So the situation is like this. This is 1, this is 2 and this midpoint is, suppose this is, we are calling as 5. So this is 5. What is this distance between 1 and 5? It is R and R, 2R. So this is 2R. What is the distance between 5 and 2? It is R and R, 2R. So what is this value? It is going to be 2 root 2R. And this 1 and 2 distance is going to be same as the distance between 2 and 3. So can I write D12, D21, D23, D32 is going to be 2 root 2R. Can I write like this? Yes. Just put all these values in this expression and you will get the GMR. You can save your time, because if you see for strand 1, 2 and 3 is same like 1 and 2 is for 3. It means if you find the GMR of 1 and GMR of 3, it is going to be same. So any one of that you can find and you can use it. Is it clear for everyone? Now you can do this question. Just tell me in the comment section, are you able to follow this or not? Yes, Ananya, Bala, tell me, are you able to follow this? Any doubt you can ask me. Is it clear? Yes, everyone. So we are running short of time. So let us stop here. The rest of the questions related to the compensation, reactive power compensation, we are going to discuss in the next class. That is going to be tomorrow, 11 AM in the morning. Okay. So let us stop here. Let us stop here. But before you leave the session, let me tell you my personal Telegram channel on BYJU'S Exam Prep, that is Electrical by Ashutosh Saxena, that is my name. So if you want, you can join this personal Telegram channel so that you remain updated for all the exams requirements, and if you have any doubt, you can directly reach out to me. Thank you so much for joining me live in the discussion. Take care of yourself and let us meet tomorrow. And tomorrow we are going to talk about reactive power compensation. I can assure you that from the next session tomorrow, 11 AM in the morning, definitely you will see 2 to 3 questions in your HPCL examination. Thank you so much. Take care of yourself. Thank you. Thank you, everyone.